Hello everyone. This video is the second part of the force oscillation. Okay. And in previous video, we already we kind of solved the particular solution or say long-term solution. We solved the long-term solution of the force equation of motion for of the force oscillations. And the very important result is we get the amplitude, and the amplitude is a function of omega. Okay, and what is omega? Okay, don't forget what's the meaning of omega. The omega is, okay, let's say, okay. The meaning of omega is applied frequency. Okay, don't forget the meaning of omega in the force oscillation is the applied frequency, applied frequency, apply FREQ, applied frequency. Because in the force oscillation, we apply a force in your system, and the applied frequency is just the omega. Okay, and right now we solve the amplitude A, and we found we found it's a function of omega. So that means your amplitude is not constant anymore. Okay. And back in very early, the simple harmonic oscillation, our amplitude is a constant, And in damped oscillation, I think amplitude is, we can view the amplitude as a function of time in damped oscillation. In damped OSC oscillation, okay, I think is A is a function of time. And it's constant A times exponential 2 tau over minus t, and 1 over tau is B over M, and the damping parameter B control the relaxation time of the damped oscillation. And now in force oscillation, right now our amplitude is a function of applied frequency. Okay, that's very important. And omega 0, that's called natural frequency. It's called natural frequency is k over m, and take a square root. And here b over m is also 1 over tau. Okay, it's the same here. Okay, so it's b over m is always 1 over tau, reciprocal of the relaxation time. And we, in the previous video, we already get a relationship. We get the phase constant phi. Okay. And when you apply frequency is not equal to natural frequency, you will have a phase lag. That means you apply the system cannot respond to you apply force immediately. Okay, there will be a lag. Okay. Okay, that's intuitive. Yeah, your system have a natural frequency omega 0, and my applied frequency is omega. If this is not the same, you cannot expect when I apply a force to a system, and the system will immediately respond. Okay, because we are not in, these two is not in the same pace. Okay, so that's the first of all. And then we are going to do a little further. Okay, we look at what's information in there. Actually, this solution, this amplitude solution, will give us lots of information. Okay, so next thing, we go to next page. Okay, next page. Okay. So we get a solution, or actually it's a solution, particular solution, a long-term solution. The long-term solution is amplitude A omega. Okay, let me just make a note here. Yeah, I think it's better to, yeah, this is, no, this one. And this big term is called A of omega. Oh, okay. And this is a solution for position, and then we can do a derivative of position with respect to time, and we get a velocity, right? Okay, we get a velocity. Okay, there actually is some algebra work. Your denominator will become like this. Okay, try it by yourself. I'm not showing every detail of this work. It's just algebra work. Okay, try it yourself. Doing derivative, and there will be a omega comes out. Okay, and then you would put omega and m into your denominator, and then this is your final. This is the result. Okay, and the derivative of sine function will become a cosine function. So this denominator, try yourself. No, it's not that difficult. Okay, and the denominator will call this called impedance. Okay, this impedance, and there's two terms in there. One is resistance, the other is called reactance. Resistance actually, this may be kind of misleading. Okay, actually resistance is B. Okay, and the reactance is M omega minus K over omega. This is reactance. This is resistance, and this you will see the same terminology like the impedance, reactance, and resistance. You will see the similar not similar. You will see the terminology in RLC circuit. Okay, this will also happen in RLC circuit. Okay. Okay, so the force oscillation, the concept shown in force oscillation will also apply in RLC circuit in the future. Okay, RLC circuit is just a force oscillation. If you have the alternative current or alternative voltage. Okay, in DC is direct. DC, I think DC is not case. So it's alternative DC, alternative current or alternative voltage. Okay, and you can check. And then the reactant resistance, actually, they are all. I think these two are all resistance. Okay, yeah, B is a damping parameter. You control the damping parameter, so it's yeah, it's a resistance of system. You higher a damping force, yeah, larger resistance. And for the M and K, I think M and K is also, yeah, it's also kind of also like another kind of resistance, because if you have a large mass, okay, if you have large mass, your system have large mass, so it's hard for you have large mass system, and you apply a force, and it's very difficult to accelerate it. Okay, so if you have large mass, that also means it's very hard to make a change on your system. So large mass, yeah, I think reactance is also kind of, it's just another word for resistance. Okay, and if your system has large force elastic constant or force constant, that means your spring is very hard. If your spring is very hard, yeah, that's the same thing. If your spring is very hard, when you apply a force in a very hard spring system, it's also difficult to make a change. Okay, that means also have large resistance. Okay, okay, so I think the K, the force constant and mass and damping parameter, they all can be treated as some kind of resistance. Okay, but I don't know why there is a different name between these. To me, they are all resistance. But I don't know why they have to make a two name for this. It's very weird. Okay. And then for this, okay, so and now and previously we showed the phase constant or lag for the force oscillation system. Actually, you can do the math by yourself. Actually, this tangent alpha, this is equal. Okay, this is equal to the resistance. And this resistance is the denominator, and numerator is reactance. So okay. You can check by yourself. These two is the same. Okay, check by yourself. Okay, convince yourself. Convince yourself. Convince. Oh, they come. Check yourself. Yeah, the phase leg, this formula and this formula, they are actually equivalents. They're equivalents to each other. Yeah, do the real check by yourself. How to check that? Yeah, the omega zero is, don't forget, the omega zero is, I write it over here. Okay, don't forget this. Omega zero is, maybe I should move this away. Okay. How to check this is this is equivalent, very simple. Okay, omega zero square is k over m. Okay, and the tau is, and 1 over tau is b over m. Okay, so if you put this to this back into this equation, back into this, you will find it's the tangent phi is equal to reactance over the resistance. check by yourself. Okay, the next thing is, okay, so we're back to from the amplitude function. What happened to the amplitude when the applied frequency is far from natural frequency? Okay, so let's discuss this amplitude function. Okay, this amplitude function, and let me write down the amplitude function. Do we have the rule to write down amplitude function? No. Okay. Yeah, I don't have the space. Maybe just do it here. Okay. So you consider the applied frequency far from natural frequency. So far from natural frequency, there's only two possibilities. What's two possibility? Far from the natural frequency. The first case is your, yeah, let's use another color. Is this better? Okay. One situation is your angular frequency is this is applied frequency. Okay, it's very small than omega. Not good color. Yeah, best one is still this or this. Yeah, like shit. Okay. Okay, the first situation is far from the natural frequency. First situation is your omega is way smaller than omega zero. And at this situation, what's your amplitude rate? Right now, just discuss amplitude function. This is, yeah, this term. Then this term. Amplitude function is function of omega. If omega is less than omega zero, what will happen? So if omega is less than, much less than omega zero, what will happen? So it will become in there. So we don't consider this because, so okay, so it will become omega 4. Mm-hmm. Mm-hmm. Yeah, let me check this. Oh, okay. It looks like it should become a omega 4. Okay, omega is way less. Sorry, my bad. Sorry, my bad. Yeah, no, my bad, my bad. Okay, no, okay, no check. Okay, okay. I found the I figured that out. Is omega very small than omega zero? That means you don't need, you can ignore this term, and that means omega is small, so you also can ignore this term. So at this situation, your amplitude function is okay. Actually, it will become, let's see, R4 omega 20 square. What will become? Okay, you will become this F0 m omega 0 square. Okay, so let's see. This is applied force magnitude. This is applied force magnitude, and this is a massive system, and it's a natural frequency. Okay, so actually, it's not function. It's not function of omega. When your omega is way smaller than natural frequency, and the a omega a is not function of omega. Function of omega. Okay, so that's when you the very low frequency, at very low frequency, your amplitude is not function of omega, and when your applied frequency is very small, that means very slow motion. Your amplitude is not a function of omega. That's the first situation, and omega is way smaller than omega zero. And we will there will be a graph to explain this. So we discuss another situation. Another situation is if your apply frequency is your applied frequency is way larger than the omega zero. Okay. And what will happen? Omega is way out larger than omega zero, way larger than natural frequency. So that means we can cancel this term. And okay, it's kind of very complicated. It will become the omega 4 minus omega square. This is more complicated. Okay, let's see. Let me write down the result directly. Maybe there's some derivation here. I hope not. Mhm. Okay, so let's see. When your omega is way omega than zero. Let's see. Yeah, do we need a calculation or some derivation here? Let's see. Our amplitude function will become, let's see, f0 over m, and this omega square root of omega square minus omega over tau square. What's this? Can we? Omega is way omega is zero. Omega will be over m. What can we do for this? Omega square. Rho square m omega square. Mm-hmm. Okay. Okay, so we can do a little modification here. F over 0 and we factor the omega out. Okay, and this will become 1 and minus this omega square. Let's see. Oh, this omega 4. Okay, this square. So actually it's omega 4. Okay. Okay, I see. I got it. Oh, got it. Okay. Okay. In the denominator, okay, let's make another color here. In the denominator, you will become omega 4 minus tau square and omega square. And right now we assume omega is a huge number. So omega 4 is way larger than omega square. Okay. And finally, we will become like this. With the result is this. Okay, result is this f0 over m omega square. So your applied frequency is way larger. Your natural frequency, your amplitude is a function of omega. So that means at a very large applied force, your amplitude is about it's about 1 over square 1 over omega square. Okay, maybe I should write here. Okay, you will be like this. Okay, your very large applied frequency, it's about 1 over square. Okay, roughly. Okay, 1 over square. That means when your frequency is very high, applied frequency is very high, you apply a very high frequency, but your amplitude decrease. Amplitude decrease. Amplitude decrease. Very strange. Okay, very strange. Very strange. Because intuitively, I say if I have applied a very high frequency to to a certain system, as I keep increasing my frequency, intuitively, intuitively, you will find maybe my amplitude frequency my amplitude will increase as a function, increase as I increase the applied frequency. It will keep increase the frequency of oscillation. The amplitude will also increase. The amplitude also will also increase. That's intuitive. That's our intuitive. But the relationship here tell you if your frequency is very high, actually your amplitude is decreased. Okay, the amplitude is a function is proportional to 1 over omega square, and omega is the applied frequency. Yeah, if you apply very high frequency, actually your amplitude decrease. Okay, that's very interesting. And it's kind of it looks like you can think this way. If you apply a very high frequency into your system, the system just ignore you. Okay, the system ignore you, and the system ignores you. The system ignore the applied force. Yeah, that's very strange. You apply a very high frequency, but the system just ignore you. Or you can think maybe the system just cannot catch up with the applied force. Okay, the system cannot catch up. Catch up to the apply force. Okay, so that's a very important. This is very important conclusion. If you apply a very high frequency into a system, the amplitude doesn't increase. On the other hand, the amplitude decrease and decrease as a function of omega's 1 over omega squared. That means your amplitude will decrease very fast if you keep increasing your apply frequency. And the other limitation is when your omega is very, very small, actually the amplitude is almost a constant. Okay, it doesn't matter. It doesn't depend on your apply frequency. But like I say, it's a if your apply frequency is way below the natural frequency, your amplitude is not a function of apply frequency. But when your apply frequency is very large, very fast, very frequently, but the amplitude decreases. The amplitude decreases. Okay, so there is a graph to show this result. Okay, it's in the next page. The next page. Okay, we just temporarily turn this off. Okay. We turn this off. Okay, let's look at this graph here. Okay, this is a very, very good graph. Okay, like I say, we just discussed your applied frequency is way below the natural frequency and way over the natural frequency. So we look at this graph. Our natural frequency maybe maybe just here. Okay, no, this is our natural frequency is here. So the horizontal is applied frequency, and here is called driven frequency, but we can so call it applied frequency. Yeah, you can call it driven frequency as well. Okay, and the y-axis is amplitude. So at the very beginning here, we see here at the very beginning, at the very very beginning, at a very low driven frequency or very low applied frequency, your amplitude is nothing. It does not increase with the driven frequency. Yeah, in the last page we just say your applied frequency way below the natural frequency. Your amplitude is not function of applied frequency. Okay, see here, it's almost a straight line here. Okay, you will increase the applied frequency, but the amplitude doesn't change. Okay, the other limit, when you apply a very high frequency, here you apply a very high frequency, you will find the amplitude decrease as a function decrease when we will find the amplitude decrease when the angular frequency increase here. See the decrease here? No matter it's red line, green line, or blue line. When the applied frequency increases, the amplitude decrease. When the driven frequency increases, the amplitude decrease. This is just what we saw. Okay, when your applied frequency is way larger than natural frequency, your amplitude is proportional to 1 over omega squared. That means decrease. When your omega goes up, amplitude goes down. Okay, see the same thing here. Okay, omega increasing, but the amplitude decreasing. Okay, see. So this formula is tell you about this is the very important conclusion. This very important conclusion from this very important conclusion from the result of the force oscillation. Okay, so we just only discuss the amplitude function, and this already give you us many information for the force oscillation. Okay, so we discussed when the applied frequency is way below natural frequency and way over the natural frequency. A very interesting question: what happens when you apply frequency equal to the natural frequency? I think that's the video. That's we are going to discuss for next PowerPoint. Okay, no, that's not next PowerPoint, next video. Okay, because I think this video is already long. Okay. Okay, so there's really lots of story for the force oscillation. Okay, lots of things we can talk about. Okay, but I think the most general physics textbook only take 1 page to talk about the force oscillation. Very strange. Okay, actually, force oscillation. There are a lot of things we can talk about in force oscillation. Okay, and the final point is, okay, this graph is just to draw the amplitude function. Okay, this graph is just draw the amplitude function, like the which page? Okay, here. Yeah, this graph is just draw this amplitude function here. Okay, this amplitude function, the amplitude function here, a omega, a omega. You draw the a omega, and you will see this graph here. And here's his setup is f0, mass, and k, and different b. Okay, different b, you have a different picture. Okay, and yeah, we haven't talked anything about the damping parameter B. Yeah, we haven't talked about anything about damping parameter. Yeah, I think we'll talk about damping parameter in the next video. Okay, in this video, just talk about, okay, way below natural frequency, your amplitude is not function of applied frequency. But if you add a very high applied frequency, your amplitude is decreased as your applied frequency increase. Okay, so we will talk about resonance in next video. Okay, and see you in the next video. Okay, bye bye. It's so long. Okay, so many things we can talk. Okay.